Hello, everybody. Welcome, welcome. All of you early birds. It's so great to see everyone. We'll get started in just a minute here. Look at everyone. So exciting. So glad to see you're all interested in advanced air pollution monitoring. Welcome in. We'll get started in just a few seconds. All right, amazing. Hello, everyone. Welcome in. My name is Sarah Viken, and I'm the Manager of Educational Programs here at the Environmental Law Institute. Thank you so much for joining us for this program on advanced air pollution monitoring, co-sponsored by the International Network for Environmental Compliance and Enforcement, or INES, and the Local Government Environmental Assistant Network, or LGEN. We have a fantastic program lined up for you today about recent developments in air quality and pollution monitoring technology, data issues, policy implications, and more. I want to take a moment to thank all of our wonderful speakers, Tim, Jane, Claudio, Peter. You'll hear more about all of them shortly, but thank you for lending us your expertise today. And a special thank you to Lee and Jerry for guiding us through today's program. I also want to thank INES and LGEN for co-sponsoring the webinar. Please check out the event webpage for more information about both of these wonderful networks. You'll hear a lot more about INES from Lee Paddock, but the Local Government Environment Assistant Network, or LGEN, provides local governments with user-friendly information on compliance with federal environmental regulations, funding strategies, and tools for advancing healthy and sustainable communities. LGEN also educates communities on local government's environmental responsibilities. Now, we will be taking audience questions later on in the webinar, so please submit any questions that you have throughout the program using Zoom's Q&A function. We'll be taking a couple after each presenter, but the bulk of the questions we'll take at the end. We also encourage you to use the chat for observations, comments, questions, but please also put those questions in the Q&A so we can easily track them. That's where we'll be pulling all of our discussion questions. Today's webinar will be recorded and will be posted on the event webpage within a few business days, along with all of the slides, all of that good stuff. And before we get started, I just want to quickly introduce our wonderful moderators. I'll read abbreviated versions of their full bios while we give everyone a minute to trickle in, but please visit the event webpage to learn more about all of our moderators and all of our speakers. Leading today's discussion will be Lee Paddock, who's a visiting scholar here at the Environmental Law Institute, where he's the managing director of INES. He's also a distinguished professorial lecturer of environmental law at the George Washington University of Law School, where he previously served as Dean of Environmental Law Studies. He'll be joined by Jerry Apondo, the founder and executive director of the Environmental Compliance Institute, where he works on the development and implementation of appropriate policy, legislative, and institutional models for sustainable development in Africa. Among his many impactful accomplishments, Jerry has worked with a number of international organizations, including the World Bank Group, UN Environment, the IUCN, IGSD, and Euroconsult Malt MacDonald, and has been involved in a number of international negotiations of multilateral environmental agreements, including the UNFCCC and the Montreal Protocol. Again, please visit the webpage to see Jerry and Lee's full bios, in addition to the rest of our panelists. Thank you all for facilitating today's program. And with that, I'll turn it over to you, Jerry and Lee, to get us started.
Thank you very much, Sarah. I am Lee Paddock, as Sarah said, Managing Director of INES, which position I've held for the last 4 years. INES was founded in the late 1980s by the Dutch and government and the U.S. Environmental Protection Agency, and remains supported by the U.S. Environmental Protection Agency. Our mission has been from the beginning to strengthen environmental compliance and enforcement programs worldwide. And we do that through capacity building and information exchange. Our focus for the last year or more, last couple of years, has been enforcement of climate laws, including HFCs, and we'll expect to do some work on methane in the next several months. On waste issues, including plastics, where we have been focusing on enforcement related to illegal movement of plastics waste, as well as compliance and enforcement provisions in the new plastics treaty negotiations. We've done work on environmental justice and on technology that can support better environmental compliance and enforcement efforts. And this seminar today or webinar today is focused on that latter issue on air pollution technology. We work regularly with enforcement networks worldwide, in Europe, in East Africa with Jerry's organization, in South Asia, in the Central and South America, and in the Australian Pacific region. We are currently in the planning stages for our 11th periodic International Enforcement Conference, which will be held in Brisbane, November 6th through the 8th, along with the Australian network ALERT. Today's we're focusing on air pollution monitoring technology. As many of you know, getting good information about air quality and about compliance with air quality requirements is a challenge in almost every part of the world. We've brought together experts from government, from the private sector, and from a leading NGO to provide an overview of the issues with air pollution monitoring, and importantly, with the new technologies that can be deployed that assist in detecting and prosecuting violations of air quality regulations. So our panelists, just in order of presentation, will be Tim Dye, who is the founder of TD Environmental, a air quality consulting organization. Jane Wallace, who is Deputy Division Director for the U.S. Environmental Protection Agency. Claudio Bellis, a Senior Scientist for the European Commission on European Commission's Joint Research Center. And finally, Peter Zazel, who's a distinguished counsel and associate vice president for clean air strategies at the Environmental Defense Fund. We'll start by having Jerry Opondo, who brought the air pollution monitoring issue as an area that INES should be focusing on, brought that to us. And he'll talk a little bit about both the air quality monitoring issues that East Africa faces and some of the technology that they're beginning to use. And following Jerry's presentation, we'll then turn the program over to Tim Dye. So Jerry, welcome, and thank you for co-moderating today with me on the program.
Thank you very much, Lee, and thanks to everyone for joining the webinar today. So besides leading the team at Environmental Compliance Institute, we coordinate the East Africa Network for Environmental Compliance and Enforcement, which is part of INES since 2010. And one of the work streams that we have been leading in Eastern Africa, basically in about 7 countries. I'm talking about Kenya, Uganda, Tanzania, Rwanda, Burundi, Ethiopia, South Sudan, Somalia, and now the Democratic Republic of Congo. That's about 8, 9. And in our part of the world, air quality management is a fairly new stream in terms of environmental regulation. It's one that for a long time was neglected, but has only gained attention over the past decade. And for that matter, Kenya happens to be the one that currently has what we could call the oldest air quality regulatory framework. And that's only about 10 years old, since 2014. And the challenge that we face in the region, even as we try to promote regulation of air pollution, is mainly on the issue of data. And for Kenya, for example, when we did put together the air quality regulations in 2014, we did not have specific country-based data to inform the decisions around air quality regulations. So what they did was mostly rely on, for example, standards from the US EPA, World Health Organization guidelines, and also look around other similar jurisdictions to just see, what are other people doing in terms of regulating air quality, and then patch things together and then come up with what they call the regulation. And this is a challenge that many countries around Africa especially face. So air quality monitoring has only gained traction over the last 5 years or so. But then again, it is limited mostly to research-based monitoring at the universities and a few cities that have attempted to do some level of monitoring. Current available technology mostly is the low-cost sensor technology that again comes with a varied set of challenges with a few regulatory grade monitors in maybe just 1 or 2 cities within East Africa. So this kind of forms the kind of background that got us to propose to INIS. This is something that would be great to have across. So we are very excited and very honored to have all of you in the webinar today, and we look forward to hearing from you. Thank you, and back to you, Lee.
Thank you, Jerry, and for outlining the important issues for Africa on air quality monitoring. We'll begin then with Tim, who's going to talk about some of the developments in air quality monitoring over the last few years and give us some background in the area. So Tim, the floor is yours. Thank you for joining us.
Great. It's a pleasure to be here, and I want to give a kind of broad overview of air quality monitoring and provide some examples of work that we're doing and others are doing that relate to some of the concepts I'm going to talk about today. So I'm going to cover really 3 thematic themes. One is kind of overview on air monitoring. I want to talk about the technology, but also the operations, and share with you some challenges that we're seeing right now. I'm from a small air quality consulting company. We work at the intersection of government agencies throughout the US and world, city, local, state, federal government, as well as community-based organizations and environmental justice groups, and do a lot of air quality monitoring and planning, and you'll see some of the work that we're doing today. It's certainly exciting times and an exciting topic to discuss. So I think one thing that's always good is to figure out, where does air monitoring fit in? We start over here with an objective of what we want to do. Oftentimes, it's really important to think about the outcome, the benefits. What are you trying to achieve? That's a difficult thing, as I'll talk about a little bit later. But where does air monitoring fit in? It fits in right here. A full air monitoring program is going to have some sensors or devices, some managing the data, people to manage the equipment. And oftentimes that is not an easy endeavor. It can take a year, 3 years, could take longer to collect all that data. And then to process that data, visualize it, interpret it, create some sort of action or intervention to address the pollution problem, and then ultimately achieve benefits. So, one of the challenges here is we can go out and monitor air quality, but it takes time to collect the data, to interpret the data, and to ultimately get some sort of action. And it's interesting, one of the things that we're seeing is some organizations are starting over here at the left saying, what is our objective? And we want to monitor air quality. And we've actually talked to them and said, hey, your objective really, you don't need to monitor the air quality. You can skip over here to action and start working on that and basically save, anywhere from 2 to 4 or 5 years of effort. And I want to share with you one example of that. This is a group that we're working with in San Jose, California. It's Latinos United for a New America. They came to a technical resource center that we run called the Bay Air Center. And they said, hey, we want to monitor air quality. And we started talking with them, and they said, we're really concerned about the traffic pollution. And we want to monitor air quality. And it turns out there was a reference station run by the Air District within their community measuring near road pollution right by the highway. And through repeated meetings and conversations, they decided we're not going to monitor. It's too complicated. What we're going to do is instead focus on building a barrier wall and focus on vegetation barriers. And so the idea was they skipped over the air monitoring and went right to the action. And that's something I see kind of more and more now, because air monitoring is complex. And so let's talk a little bit about air monitoring. There are a number of things here, right? There's equipment, so the technology, what equipment are you using? Is it certified? Is it accurate? Is it reliable, sensitive, durable, suitable, whatever that is? And it's complex stuff. But I want to argue that the more complex thing is over here on the right. Instead of technology, let's talk about people. Let's talk about where people are going to locate things, who's going to maintain it, who's going to do the quality assurance, the data handling, the verification, the quality control, the reporting. And if you look at successful projects, and we run a bunch of them, the time that's spent or the budget that's spent on the equipment should really be less than 20%, substantially, even less than that. And most of the effort and budget and time and money should be invested in people in the operations. And this is one of the things that we see people getting wrong all over the places. Too much money is put into the technology. There's not enough money going into the people and the use of the equipment. And so when we think about technology, let's also remember that that's just a portion of it. The operations are really critical. There are lots of different equipment out there, from vans that are on the order of $500,000 to $1 million that can drive around and sniff out things. But it requires, again, people experts to measure that. There are new technologies like remote sensors that can measure pollutants along a fence line of an industrial area or a refinery, for example. Those are, on the order of $200,000 US. It still requires expert, but it can give, really good information if the plume drifts right through that narrow beam along the fence line. The other thing, and this is really the mainstay around the world, is reference instruments that are run by regulatory air quality agencies. An individual instrument in here measuring one pollutant is about $20,000, but you still need the people, the experts, to run it. We also see emerging equipment, portable equipment that can be moved around. That's good. You still need an expert to run that. These can be quite accurate. They're nice because they can be moved around to different locations. And then lastly, we have air sensors. And I know, one of our speakers is going to talk about that. And the air sensors are, some of them work quite well, some of them don't work. But the nice thing is they can be used by anyone. But again, remember that kind of 80-20 rule that I mentioned. In my last slide, I'm going to talk about that and share with you an example. Other aspects of monitoring are like, is it fixed or is it mobile? Is it moving around? Are we covering a particular area, like a neighborhood? Are we covering like a refinery or industrial area? Are we looking at personal exposure? And one of the big changes we see right now is more of a focus on holistic air. Doesn't matter if it's inside or outside. People are very interested in measuring what are we exposed to and measuring both inside and outside air. And we're doing a neat project in Los Angeles, looking at recreational centers and air inside and outside and delivering kind of holistic picture of what's going on. As I mentioned with the people, operations is critical. These are all the steps that we kind of recommend, and we put together a 5-part webinar series. I'll drop that in the chat during after my talk, that talks all about how to do this. And these are some of the things that people need to do. Developing a monitoring objective. Oftentimes that's not done. It's a critical thing. Setting up data management, developing a plan. Number 4, or a quality assurance plan, determining where you're going to put the equipment, installing and maintaining the sites, analyzing, communicating. All this involves a lot of planning, a lot of effort, and a lot of people time. So I want to switch now and talk about some of the challenges and give you some real world kind of things that are going on. One is air quality is exceedingly complex. It's complex for a number of reasons. We're dealing with different pollutants that are affected by the weather and they move around. We're dealing with a variety of different sources that are controlled by many different jurisdictions. And it's not easy to find out who controls what. We're also in a world where there's regulation and policies are changing. So we're dealing with kind of a complex topic. The other thing, and I think this is really substantial, is there are major demographic changes happening in what I call the air quality ecosystem. There are retirements from folks that have worked in this industry for 30, 40, 50 years. There's also, and this is great, hiring whole new workforces, coming in and learning lots of new things and bringing new energy and new ideas. So big changing workforce. The other thing that's happening is an increase in funding with new organizations and people being brought into air quality for the first time. All of this is leading to something that's really, I think, important, is to talk about fundamental information. And this is something that we're doing. We run these all about air quality boot camps. This is in partnership with Coalition for Clean Air, and this is funded by the California Air Resources Board. These are 2-day intensive workshops designed for and given to community-based organizations, environmental justice groups. We bring them in, it's a safe space. We have enough time to cover everything from what's in the air, what the pollutants are, the health effects, the sources, the modeling, the measurements, how do you advocate for better air, who controls what. All of that is covered in 2 days. And we've gotten great feedback about this. We've also done this where we've done simultaneous translation back and forth with English and Spanish, and that's been wonderful as well. Next challenge that we see, and this is a huge one, is what are the objectives? What is the purpose for monitoring? And really thinking that through. And that becomes really important when you try and determine who's going to be involved in the project and what technology you're going to use. And this is an area where we see things really going awry, is not spending enough time up front asking the questions. Why are we doing this? What do we really want to achieve? And how will monitoring fit in and help us achieve our objective? And so spending, a good portion of your budget, on this objective right in the beginning is really critical. This is a project that we're doing where we actually did that. The group was interested in, this is the Navajo, a Tri-Chapter Council of the Navajo Nation. So this is in kind of the southwestern United States. There's a project we're doing, it's called AQ Earth, and we're working with the National Institutes of Health. They originally came to us and said, we're concerned about methane and oil and gas production. So we made some measurements and decided, the technology would not be able to capture and detect that. So we pivoted and said, what is your next objective? Their next objective was to look at ozone transport into and out of their region from distant locations. And so we designed a network to actually quantify that and measure that, to detect what's coming in and what's leaving this particular area. And so we spent a lot of time focusing on that objective, and it's great to have a really clear and crisp objective. Next thing we see, and I'm sure we're going to hear other speakers talk about this, data quality becomes really critically important for any air monitoring program. There's lots that goes into this, as we can see over on the left here. If we have really high quality data, we have more certainty. It can be used for a variety of applications. If the quality is not as well known, we have less confidence and there's fewer applications that we can use that data in. I want to share with you, one example, and this is a environmental justice group, Green Action in near San Francisco, California. They are collecting data, and this is showing their site here. This is a year's worth of data, and the green shows where we have the instruments, the sensors were running. And these, albeit, are difficult sensors to run. Lots of gaps, lots of downtime. So someone could look at this and they could say, there's not enough data there. We can't answer any questions with that. But one of the things we want to do is say, well, what could we do? And so we started zooming in on a period where we did have some more complete data. And we were able to look at and compare sites and see which sites are higher, which sites are lower. But again, data quality is really, really important. It gets back to that kind of 80-20 rule, spending a lot more time on people planning and focus on data quality. Towards the end here, I want to talk a little bit about data access and ownership. How will you or how can you get, download, and use your data is becoming more and more important. Many of these devices produce a lot of data. It's sometimes hard to get. Another thing that's critically important is data ownership. Who owns the data and who has rights to use this data? Just because you buy a piece of equipment or maybe lease it, you may get the data, but you may not own it, or there may be joint ownership and that data can be used by perhaps the vendor or others. So making sure this is really clear right up front when purchasing equipment. I want to share with you a project that we did in Indore, India. This is USAID funded. It's a project called Building Healthy Cities with JSI. And the goal here, in Indore, there was one reference station, and this project put in 20 PM2.5 sensors. And from the beginning, we decided and really lived up to that ratio, the 80-20 ratio, and it was about 10% was spent on the hardware and software and about 90% on the people. And one of the things that we really focused on is data, access to data, and who has the data. We wanted that access to be available to the clean air guides that are shown here so that they could get the data, go out and do work within their particular communities, educational work, awareness work, and also intervention work to address things at local sources that are producing particulate matter in that area. This is a super successful project. If you're interested, I can drop me a line and I can send you a report from this project. Lastly, I just wanted to thank everyone. Looking forward to some of the questions. We're an organization, we work a lot with community-based organizations. We understand government as well, and we're independent. We don't represent any instrument company or any device company, and are super creative and technically rigorous. So thank you, and look forward to the questions.
So we do have a couple of quick questions, Tim, that we can ask now and before we move on to Jane. So there was a question about modeling and monitoring and how they interrelate. The question says, one of the things that we're seeing at the state and local level is that there is not adequate air quality data. So the state bases their policies and regulations more on modeling. The claim from some environmental groups is that the modeling is not accurate. How should monitoring fit into this situation? So what might be your experience in kind of figuring out how much you rely on monitoring versus modeling?
I think you're going to need both. I mean, if you go back and look at the weather community, if you look at the air quality community for the last, 30 to 40 years, there's been monitoring data that's been collected that's used to evaluate, how the model's doing. We need that validation. And so that's absolutely critical to have both of those. One cannot kind of supplant the other.
And I think there's a total of 3 questions, so maybe we can get through all of these. So how do state and local governments quantify or justify the benefit of air quality monitoring? Good air quality monitoring is expensive and takes time to see the benefit. So Do you have some experience about how to best make the case for the 80% that's needed to ensure you have good programs?
Yeah, I mean, I think, and I'm sure some of the other speakers would talk about this, is just the quality. It's important, one, to spend the money to get quality data. Two, if we can't manage anything that we don't really measure. And if you look at, and I know the US EPA has a great chart that shows progress over the last 40 years, where many of the pollutants through regulations and policies, those sources have been reduced, and you can see in the atmosphere a reduction of pollutants, ozone, PM 2.5, PM 10, and lead. We know that because it's measured out there, throughout the country. And so without those measurements, we wouldn't know if the policies or the regulations are working. And so it's critical to have those kind of independent measurements.
And there are a few other questions. I'll just note one more, and then we can take up additional questions at the end of the presentation. So this is a question about purple air monitoring for particulates. And the questioner asks, is there a similar device, ease of use and cost to monitor for VOCs at a detection level that would produce positive detection in fence line communities?
There's not. I wish there was. We've tried a bunch, and you look at the data, it's noisy. You may see a spike, but it's hard to identify what that is, if it's even real. I would not waste time. I've also said that, in the past, some of the lower cost VOC sensors are garbage. I would not waste time with those right now. Things may change, technology changes. We are in an ever-changing landscape. So, but right now, I would not spend time focusing on that. The other thing too about purple airs is purple airs work great for PM 2.5. They don't work for PM 10. They report PM 10, but it's not measuring PM 10. And so, I know one of our speakers, Claudio, works at a research center that has done, foundational, fundamental work with these devices for well over a decade, maybe 15 years, and could certainly talk about that. So.
Good. Well, thank you, Tim. And we'll now turn to Jane Wallace from EPA.
Thank you, Tim. Thank you, Lee. Tim, that was great foundational understanding of the what and how of monitoring quality and the challenges around this space. Thank you for INEC to invite the EPA to be part of this panel. I am Jane Wallace, the Director for the Enforcement Targeting and Data Division. We hold the data and provide training for the EPA's National Compliance Monitoring Program, which includes targeting, data analytics, inspections, and development of tools that support the Office of Enforcement and Compliance through transparency. Again, thank you for giving us an opportunity to join in this discussion. In our prep meetings, it was clear that the EPA can provide some insight based on our experience in this area. And as Jerry described at the start, it's helpful to know that others are looking to the EPA with our work and experience. And we will share some of that work and what we're doing and where we're headed. Next slide, please. Oh, thank you, Sarah. So in this one, in terms of context, the EPA publishes yearly data on hazardous air pollutants and criteria air pollutants in the air quality system. This system is EPA's repository of ambient air data quality that assists in air quality assessments, designations, modeling for permit review, and preparing reports for Congress as mandated by the Clean Air Act. The Ambient Monitoring Archive combines hazardous air pollutant data with other data sources, many of which are specific to localized areas. The Ambient Monitoring Archive has historical data going way back to the 1990s, housing over 100 million data records with over 5,000 monitoring sites. As you can see on this map, this shows all of the air quality system historic monitoring sites, both the active and inactive ones. Next slide. EPA uses monitoring data for enforcement, targeting, and compliance. Monitoring data are also combined with facility reported emissions data into the air toxic screening assessment, which we lovingly call the air toxic screen. This is EPA's screening tool that provides communities with information on health risks from air toxics. EPA enforcement uses this tool to identify risk hotspots, which are areas of elevated cancer risk or higher potential for other health impacts. Enforcement then screens those facilities in those areas where the measured pollutant concentrations are larger than expected amount, potentially revealing facilities needing further evaluation as it could be indicative of underreporting emissions. These images show how stationary monitors are depicted at several levels. The one on the upper right hand shows potential areas of interest from a US national view, and then drilling down to a 10-mile or 16-kilometer radius, which is the blue map on the lower left-hand side. You can see the same sort of blue, yellow, orange, and red zones, which are intended to depict an increasing risk for hotspots. And then a further drilling down to 2 miles, or I think it's 5 kilometers in the lower right-hand map, shows how each monitor reflects that risk score. So you're seeing either nothing or numbers going up. It's just an indicator. Next slide. Our office has a vested interest in keeping up to date on technology and the support it can provide in identifying environmental problems. And Tim did a great job describing that. We are cognizant of the risks in data gaps, quality, black box effect from algorithms, bias encoding, all that kind of stuff. Those have also been outlined in the White House's executive order on the use of AI. I believe, and I know that there's guidance being provided by the Office of Management and Budget that gives us guidance on governance and innovation through artificial intelligence. Technology is rapidly evolving, allowing monitors to move and collect large amounts of data across a wider geographic space. Some of those technologies include, and you saw that picture again from Tim, I love his slides, geospatial monitoring of air pollution, vehicles that measure pollutant concentrations from a van, drones, flyovers, and wearable monitors, satellite imagery, fence line monitoring, community ambient monitoring data by other entities. We do develop our analysis on a services-based approach. So when we need to pivot on the interpretation of that information, such as environmental justice, which has moved away from a race-based index, we are able to apply new indexes relatively easily. I'm not going to say it's super fast, but we do it rather quickly. That allows us to focus on the programmatic issue or administrative priorities. In the area of environmental justice, consideration for population under a poverty line is a factor because the ability to move away from an area is low. The way that when cumulative risk is identified, focus should be in those areas. We recognize that monitoring is important. Having a lot of data can be overwhelming, but as the technology advances, large amounts of data can easily be processed to provide actionable information. In some cases, this serves as an additional data point, but having the ability to transform that data, whether it's an interpretation or a visualization, helps in focusing our EPA's limited resources, such as our inspectors. We also recognize issues of lack of data. In cases of environmental justice, it's hard to interpret or project issues, specifically in tribal areas. So we are looking at potential marginalized communities, or those that live in sort of that cross-sectional world, the very young, the very old, in rural areas or below certain thresholds of income. You get the idea. That way we can start telling the stories of those that are excluded from our data. Again, there is a huge risk here because there's no clear extrapolation that can be done, and the inherent bias in algorithms developed must be overcome to ensure the protection of privacy and security. Next slide. There are some issues that come up coming from work that the EPA is performing. I'm sorry, there's more of these things that were coming up and we're looking as EPA is working. We are developing data portals to process and visualize data. EPA is soon launching a methane super emitter program, a program where third-party notifiers such as satellite companies can inform the EPA of methane leaks. And EPA will then notify the owners or operators of those facilities that are leaking. EPA has a mobile van program that has operated since about 2005 and is expanding to include more vans, increasing our ability to monitor air pollution anywhere there is a road network in the United States. So that kind of excludes Alaska and Hawaii simply because we don't have vans there. EPA is issuing regulations that require monitoring at boundaries, focusing on specific industries for multiple pollutants. EPA is looking into the future for larger data sets, and this includes several monitoring platforms, looking at wider geographic coverage, the ability to leverage more real-time results. All of this gives us a clearer picture of pollution. Monitoring is intended to hold facilities accountable while protecting vulnerable communities. Fence line monitoring is meant to detect fugitive emissions and protect communities near facilities. EPA has developed a visualization dashboard for benzene emissions from petroleum refineries and aims to develop similar tools, visualizing the future for fence line pollutant measurements. With that, any questions? It's hard to scroll, there's a lot, right?
Okay, so go ahead, Jerry.
Thank you, Jane, for that very elaborate
A
presentation.
lot in a very, condensed manner.
Quite informative. So there are several questions, but I think we will just take perhaps 3. And the first one is with respect to national air quality regulations, who pays for the monitors? I think that's an overlap from the previous one. So is it mostly the state or metro area, or does the EPA provide some funding for purchase of the equipment and or operations?
Oh, that's a great question. I put on the spot. I'm not sure I know the answer, and I hate to put Cora on the spot. Cora, do you happen to know the answer to this question?
Everyone, I think it is definitely a mixture of federal monitors and state monitors. So there's a lot of state monitoring data that's contributed to the air quality system, and that makes its way into air tox screen in the ambient monitoring archive. So it's definitely a mixture of both. Considering where the funding's coming from, I can't speak on that, but you can let us know who's asking that question and we can refer it to the Office of Air and Radiation. They handle a lot of the grant funding. But in terms of the data that we use, we're kind of intaking it from the Office of Air and Radiation, but thanks for the question.
Thanks. And
thank
to
you.
clarify a little bit more, we do collect data from very localized places as well. So we do take advantage of monitors that are available and can provide us quality data.
Thank you. The next question, how does EPA address stationary monitors that are not downwind of known sources and thus do not detect pollution that is known to be happening 24/7? How do you incorporate windrows and predominant wind direction patterns in locating monitors?
So, and again, I'm offering Cora the opportunity, correct me if I'm wrong, but we are developing these types of detections and patterns through visualization efforts. We not only reflect the monitors and their location and the data around it, but also depict the windrows on top of it, or that way we can start detecting those potential issues. It is not completely, thorough, but we are testing and developing those situations. Cora, do I have it generally right?
Yeah, absolutely. And I'd also add that we have a tool called the Echo Clean Air Tracking Tool. I can post the link in the chat. And within that tool, you can see all of the monitors that we have and nearby facilities, and there are windrows and wind direction components based on every monitor for specific pollutants. So we don't use to my knowledge, Winrose is to choose locations of the monitors, but we reference nearby facilities as a targeting tool.
Thank you. There are a couple of additional questions, but I'll ask the last one, and then the rest we can leave to the end or towards the end of the webinar. So is the data from EPA's mobile van monitoring program publicly available?
Go ahead, Cora.
Sure. It is not publicly available. This is currently an enforcement targeting tool. However, there has been funding from the IRA funds, and those data will be publicly available. We don't have a timeline on that, but it will be part of a future dashboard that EPA is developing with publicly available data about GMAP, geospatial monitoring air pollution van drives. So we're excited about that dashboard, and we'll let everybody know when it becomes available.
Thanks,
Jane,
Cora.
thank you, Cora. And back to you, Lee.
Thank you.
Thank you. And we'll now turn the program over to Claudia, who will talk about developments in air pollution monitoring and research in the European Union. Claudia, thank you for joining us.
Thank you, Lee. It's a pleasure to be here. Yes, I'm a senior scientist at the Joint Research Center of the European Commission. I'm working in the unit Clean Air and Climate. And yeah, I have many years of experience of both measurements and modeling of air pollution, either in Europe and also globally. Next slide, please. Could we move to, I take advantage, of the help of the, thanks a lot. And this presentation is about low-cost sensors, what were already mentioned by Tim in his presentation. The presentation is pretty technical. Next slide, please. So I will be talking about the characteristics of the low-cost sensors, the technologies, the obstacles, and how they can be applied. So next slide, let's move to the first part. So what is a gaseous sensor? A gaseous sensor acts as the amplifier in an audio system, which amplifies the signal coming from a microphone and send it to the loudspeaker. Next slide. But instead of amplifying the input signal, they transform a variation in concentration in a human-readable signal. Basically, any gaseous sensor is divided into parts, the reactive interface and the transducer. The reactive interface is a body which reacts to a physical chemical change. The transducer converts the energy from one form to another. In the analogical sector, which is the most common type of gaseous sensor, it converts the concentration variation in small electrical changes. Let's move to the next slide. So I'm talking about different technologies. So you can see here in the slide the main types of low-cost sensors. So the two most known types are also the most widely used, are metal oxides and electrochemical sensors. Metal oxide sensors are based on the variation of the electrical resistance to the sensitive layer. Electrical chemical sensors can be amperometric or potentiometric. In both cases, the sensor mechanism is based on a chemical reaction between the reactive interface and the target gas. The two types can be used for different inorganic gases like ozone or nitrogen dioxide, or organic gases like VOC. That includes VOC stands for volatile organic compounds, so it's a mixture of many type of compounds, but could be also specific for compounds like benzene or formaldehyde. Other technology exists, but for specific compounds, like for example photoionization detectors that are used for particular, as I said, VOCs, so the organic part. Finally, sensors can be aggregated in a device named an electronic nose or e-nose in sensor arrays. When talking of sensor, different characteristics should be considered that are listed at the bottom of the slide. And the most important of which are highlighted. So the sensitivity, so is the change of the measured signal per analyte concentration unit. This parameter is sometimes confused with the detection limit. The selectivity refers to the characteristics that determine whether a sensor can respond selectivity to a group of analytes or even specifically to a single analyte. Stability is another property, who is the ability of a sensor to provide reproducible results for a certain period of time. This includes retaining the sensitivity, the selectivity, the response, and recovery over time. And another important aspect of sensor is the limit of detection. So it's the lowest concentration of the analyte in different form, different from the absence of the substance that can be detected by the sensor under given conditions, particularly are the given temperature, humidity, air matrix, etc. Generally, the detection is computed as 3 times the standard deviation of the response of sensor measured in air mixture without the analyte of interest. Then there are other properties, but I mean, I don't want to get too technical, so in case we can come back to those. So I will move to the next slide. So where we're going to explain every type of sensor one by one. So the first type of the sensor I mentioned before is also the most used one in the resistive sensors or metal oxide. This sensor is made from different layers, each with a specific purpose. The sensitive body is made of a metal oxide layer. Typically, tin oxide is the most used because it has a wide reactivity and strong change on resistance. The model widely accepted is that tin oxide form grains, and the boundary of those grains dominate the conductivity. In presence of an oxidizing gas, normally oxygen in ambient air, the gas molecules react with tin oxide, trapping electrons on the surface, creating a positive charge space that acts as a barrier for the conductivity. There are, as you can see in the figure, there are interdigitalized electrodes in blue in the schema. They measure the change of resistance due to the change of concentration in the pollutant. There is a heater electrode. In fact, sensors need high temperature for the reaction to take place and a faster rate. This electrode is also used to operate the sensor with temperature pattern, but this is of interest when you need to measure the data of the sensor. Finally, there is a substrate, which is represented in gray in the figure, which is general use for electrical and thermal insulation. This category of sensor is generally very low cost. We are talking about $10–15 each. They react to a wide range of concentrations from ppm, which is part per million, down to ppb, which is part per billion levels. And they aren't affected by ambient temperature or relative humidity changes. However, they suffer from different effects. From an electronic point of view, they are power consuming due to the need of high temperature. For the data quality point of view, they generally are slow. They take several minutes to provide a signal. And their response is affected by hysteresis, which is the difference in the response when the concentration are increasing or decreasing. And finally, they are not selective. In fact, they have the tendency to react to any type of molecule, organics, inorganics, or VOC, which makes them very difficult to use in ambient air. The second type of sensor, it's in the next slide, please. These are the electrochemical ones, which, as I anticipated, can function with 2 different principles: the potentiometric, which measure changes in voltages, while the amperometric sensors, the concentrations of pollutant causes an oxidoreduction reaction in the sensitive body, which is characterized by a variation of current in amperes, and they are the most commonly used type of electrochemical cell. Every electrochemical sensor is composed of 3 electrodes: the sensing or the working electrode, the reference, and the counter electrodes, placed in a common electrolyte. The gas to be measured diffuses into the sensor and to the measured electrode, where a direct electron transfer or a chemical reaction leading to an electrochemical process is taking place. This reaction produces an internal current which can be measured. These kind of sensors are in generally of medium range price, so between $100 and $180. And as for the resistive sensor, they react to a wide range of concentration. So sometimes from ppm, so part per million, down to ppb, part per billion levels. So they are able to detect very low levels of pollutants. They are low power, and as they don't need a permanent current to activate the chemical reaction. And they are pretty fast, so they react in a matter of seconds. And generally, they have a low detection limit, the lowest concentration the sensor is able to distinguish. However, they have some weaknesses which affect the quality of their measurements. The partially selective, so from example, equal reactivity towards ozone and nitrogen dioxide. They are highly affected by changes in temperatures and relative humidity of the sampling air, and some sensors suffer from wind or pressure interference. The third type is in the next slide, is the photoionization detector, which is nowadays more and more used, in particular for organics. In practice, the PID, photoionization detector, or PID, emits UV light with a known energy. This UV light excites the molecules, resulting in a temporary loss of electrons in the molecules and the formation of positively charged ions. The gas becomes electrically charged, and the ions produce an electric current, which is the signal output of the detector. The ions recombine after passing the detector to form their original molecules. The energy of the UV light depends on the gas used, which are in general xenon, deuterium, krypton, or argon. The most common lamp is the Krypton 1, 10.6 electron volt, with a suitable equilibrium between sensitivity and selectivity. They are generally in the medium range price and only suffer from a small dependence from temperature and relative humidity. They have a fast response time, few to 10 seconds, and they are highly sensitive. However, they are highly power consuming, about 100 milliwatts, and their range of concentration is generally in the ppm range, so relatively high, with few devices able to measure down to 50 ppb. There are two main weaknesses that are they are short-term drift, and above all, their lack of selectivity. In fact, they aren't selective at all, as they measure all molecules with a ionization potential lower than the lamp energy. Move to the next slide, please. So finally, I say a few words about the optical particle counter, which is a completely different type of sensor. In this case, is used for measuring particulate matter, and the principle is based on the measurement of the light scattered by the particles in the sample. These sensors are intrinsically not able to differentiate the particle by their masses, but they determine their number and size. And the major part use lasers, since the high-intensity light source is needed to illuminate the particles. They are usually very fast in response, but the quality of the measurement depends on uncontrolled parameters such as the shape, the colors of the particles, but also relative humidity, in particular when the rates of humidity are very high. Next slide, please. So combining several simple sensors of different types can be used to improve sensor characteristics, in particular sensitivity. This type of device in which more sensors are combined is called sensor array, and they are often part of devices called electrognosis or e-gnosis. They generally use smart pattern recognition software, often based on neural networks. Single sensors don't need to be individually high selective towards a given gas. Instead, the collection of sensors should contain as much chemical diversity as possible, so the sensor array responds to largest possible cross-section of molecules. A distinct pattern of responses produced over the collection of sensors in the array can provide a fingerprint that allows classification and identification of the sample. The in-house systems are not expected to be readily applicable for accurate quantitative measurement of certain compounds like benzene, for example. Another peculiarity of this type of device is that they're very expensive because their cost range between $20,000 to $100,000 in Europe, United States, and Japan. Let's move to the next slide, please. So this chart represents the change of sensitivity of the commercially available sensors, which are current use, for example, for VOC measurement in this case. This is a summary of a JRC paper that you can find the citation at the bottom of the slide. And in this paper, the JRC reviewed more than 50 sensors or sensor-based devices, which include photoionization detector, they're represented in the dark red on the left side of the slide. We have OEM stands for original equipment manufacturer. Then we have the metal oxide sensor represented in blue and parametric cells represented in green, portable device based on PID sensors in yellow and portable gas chromatograph represented in pink, and finally in-nose represented in khaki. Our review showed that in general the PID sensor are devices sensitive but not selective enough, as schematized at the top of the group of 4 orbs you see on the top of the slide. The color represent from green okay to red not okay. Metal oxides and parametric sensor are generally not enough sensitive for measuring level of ppb or ppts, while portable PID may be an alternative, but as for the portable gas chromatography methodology, they are very expensive. Next slide, please. So one main obstacle, next slide. One of the problematic issue when dealing with low-cost sensor is their calibration, so that they provide measurements comparable with reference methodology, which are the one most accurate and mandatory for official monitoring networks. The calibration techniques range from linear regression, which is by comparison of the sensor with for a single parameter with a single a reference instrument. We have also techniques based on multilinear regression that are carried out in laboratory experiments to measure more parameters at once. And we have also the use of networks to calibrate several parameters and several pollutants at once. In the figure, we observe different curves are obtained with different methods for the calibration of an ozone sensor, as an example. In addition, it's important to mention that the calibration should be carried out regularly because sensor response tends to change in time with what we call drift. Next slide, please. Sensor-based application. So what can we do? How the sensors are used? And here we see some examples. Low-cost sensors can be used to build up low-cost monitoring stations. Due to their small size and weight, they can be installed also on vehicles or even in bikes to monitor the exposure of passenger or riders. They can be used to perform mobile measurements, as already mentioned in the previous presentations, to characterize pollution level in streets, for example, if they are mounted in buses of the public transport service. Next slide, please. The small size make low-cost sensor also suitable for measuring personal exposure 24/7, as these can be followed the user the whole day, even when they move from one ambient to the others, which is not possible to do with bigger devices that are either dedicated to indoor or ambient air pollution. And next slide, another, let's say, common that was already mentioned. So the fact that there are open source platform which offer the chance of a personalized pollution monitoring service by providing units with an array of sensors connected online, and the data elaboration is made in a centralized server. often the geolocalized data of many users can be visualized online in maps, and there are many examples of this, like the one you see in the slide, like the WASP mode, Smart Citizen, Air Quality Egg, AirSense EU, which was developed in a project in which the JRC was involved. And with this slide, I would like to thank, next slide please, to finish my presentation, and thank you for your attention.
Thank you very much, Claudio, for that elaborate presentation, especially on the aspect of local sensors. I guess we have a few questions for you. One is, could you briefly provide a discussion or a description of the size of some of the sensors you talk about?
Well, the sensors are really small. We are talking about centimeters to sometimes even below the centimeter size for the single sensor. So they're really very small. Maybe the ones of bigger dimension are the optical particle count, because this implies there is a cell where the air should circulate in order to the laser beam to hit them. So maybe the optical particle counters are the bigger ones, but in general, we are talking about a few centimeters.
Thank you very much for that response. The next question is, won't the use of neural networks for electronic noise create problems with the potential recognition of out-of-distribution molecules or chemicals in the air?
I didn't understand well the question. Could you repeat, please? So could create problem for what? Sorry.
So the question is, won't the use of neural networks for electric noises create problems with the potential recognition of out-of-distribution molecules or chemicals in the air?
Well, I would rather say the contrary. So the neural networks are more flexible and they are able to recognize better patterns, but the only warning is that they require a very high amount of data. So, but this is something I'm just describing what is the trend. So this is something that is becoming more and more common, the use of neural network, or so-called AI, for identification of patterns. And in this way, so as I said, in the combination of many different types of sensors in one single array makes it possible to overcome the limitation of the single technologies, but let's say the analysis is able to recognize patterns and how the different sensors react, and so combine the reaction of more than one sensor to describe a fingerprint for specific compounds. I don't know if I answered the question, but I mean, I hope I got the point. If not, just I will happy to clarify.
Thanks for that. And finally, it's about the gas chromatography sensors. And the question is, can you talk more about the portable gas chromatography sensors? Are they able to speciate pollutants, for example?
Yeah, well, the gas chromatograph are instruments that are normally located in laboratories or are very big. Nevertheless, they have been developed some options that are transportable, but are still, as I said, are high grade, but are extremely expensive. So I didn't went much through this, because these are research instrumentation, more for research than for, let's say, use by citizens, because cannot be classified as low cost. So, but of course they are among the ones that have the best capabilities of detection in terms of distinction of different compounds and also the detection levels.
And could you say something about the error bars that you attributed earlier on around these types of equipment?
Pardon, the I cannot hear well.
The question says, you suggested there are large error bars around the measurements, but are those error bars likely to be smaller or larger than the techniques currently used to estimate emissions?
Well, the low cost, there is a compromise. I mean, the low cost sensors are more accessible, so a lot of people can use them, but the problem is that the accuracy is lower than the reference technique. So the networks that were presented before, run by EPA or by institution where there are experts, and there are instrumentation, first of all, that is the reference instrumentation fulfill the requirements of technical standards, and require a lot of work in order to be calibrated and to be comparable to the measurements in other locations. And these are the official networks. So we use low-cost sensors to try to reproduce this as much as possible. But of course, the reduction in price comes with some, let's say, losses from the point of view of the quality of the data. And so it is important to know what are the limitations. So the uncertainty associated with the low-cost sensor is normally higher compared to reference instrumentation that is used in the official monitoring networks. This can be with a very complete and very, let's say, intensive data treatment. Some of the error can be corrected, but not all of them. So we have the problem, as we said, that some sensors are not able to distinguish between two compounds. So sensor I mentioned in the case that react the same way for ozone or nitrogen dioxide. So you cannot be 100% sure which of the two compounds are there. We have problem of the detection levels. Sometimes if the detection levels are high, you cannot see when the levels of pollution go below a certain concentration, the detector is not able to see. And other problem, as I said, is the drift. So the fact that the response of the instrument changes over time. So when you test, it reacts in one way, but if after 1 week, the sensor will react differently. And there are also interference, like, for example, we know that optical particle counters that are measured are used for particles, they are very sensitive to humidity. So they tend also when the levels of humidity in the ambient air are very high, this can lead to distortions of the measurement. So there are a lot of factors to take into account when using low-cost sensors, and it's important that the user are aware of them, and of course services that elaborate data in a centralized manner and correct all these kind of possible errors is very important, because I mean the single
Maybe I could ask one
citizen.
additional question.
Yeah, sorry.
It's
Maybe I went too long, sorry.
This is quite, I wanted to ask one additional question, and that is, can you tell us a little bit about which of the types of sensors or sensors you've talked about are proving most useful to field personnel, let's say government field personnel, in two areas? One is identify a potential problem area, and the second would be more accurate data that might be needed to support an enforcement action. Are you seeing any trends in how these particular technologies can be used in the field or are effective in the field?
This is a very good question, because in fact, the fact that low-cost sensor have higher uncertainty, or let's say lower reliability, doesn't mean that they are not useful, because of course you can deploy many of them. So this allows, for example, to create maps and to monitorize areas where the official monitoring network cannot reach, because we've seen that the network of the US is very dense, but it's also true that cannot get everywhere. So and I think that the low-cost sensor it's not an alternative, but is complementary, and it may identify situation of, let's say, with very specific regions, or with very short time duration that are not visible to the official monitoring network, and maybe highlight the need for more specific monitoring campaigns with, let's say, scientific level instrumentation, with higher quality instrumentation that are able, and of course managed by experts, that are able then to enter into the program and identify and, let's say, analyze more in detail the situation. But indeed, the low-cost sensor could be useful for that. So that's indeed a very important, and the fact that it can be where for personal exposure. Again, that's very useful frontier for the use of low-cost sensors, because I mean, we know that, let's say, the reference instrumentation is too big, so you cannot walk around with instrumentation of several kilograms. Now all this can be only done with low-cost sensors, and this is also a very important application.
Great, thank you very much, and thank you for your presentation. So we'll now turn it over to Peter, who will talk about the work that is occurring more frequently now in the nonprofit sector on monitoring, and specifically the work of the Environmental Defense Fund.
Thanks so much, Lee, and thank you all for the opportunity to be here today. My name's Peter Zalzal, and I'm an attorney and Associate Vice President for Clean Air Strategies at Environmental Defense Fund. And so as part of that, my work at EDF focuses on advancing solutions to reduce climate and air pollution from major industrial sources. So the oil and gas sector, petrochemical facilities, the transportation sector, and the like. And as part of that work, I have an opportunity to work closely with EDF scientists who recently have been deploying advanced monitoring solutions to measure methane and other air pollutants over time. And so what I'd like to do today, as Lee mentioned, is to share some of the work that EDF is doing in this space, really with a focus on advanced methane monitoring and air pollution monitoring, to discuss some of the other recent developments that we see as very important in advancing the increased availability of advanced monitoring solutions here in the US. And then to close and talk a little bit about the policy nexus here and how the data that a number of different folks are collecting can help support compliance enforcement and can actually be really woven into the fabric of clean air strategies and policies. So I'd like to start with some of the work that EDF has been doing recently to deploy advanced monitoring solutions, both for methane and for air pollutants. So two examples to share on the methane front. One is methane, our methane air campaign. And this was an effort that EDF undertook in partnership with Harvard and the Smithsonian Astrophysical Observatory to deploy advanced sensing technology aboard a jet to track methane emissions from oil and gas operations in other sectors. So this remote sensing device was flown at over 40,000 feet, and the goal was to cover 80% of US onshore oil and gas producing regions. These flights occurred in 2023, and the technology that was used is the same technology that is now aboard the methane satellite that EDF launched in March of 2024. That was the other monitoring approach that I wanted to highlight. That satellite is currently in orbit now and has a point source detection threshold of 500 kilograms per hour. And the goal of it is to provide relatively high spatial resolution as compared to some other satellites that are currently capturing and deploying data. So a little bit more on the methane air experience that we had. So again, these were a discrete set of flights There were 32 of them in 2023. You can see on this slide the oil and gas basins that were covered by the surveys and the daily coverage of those flights and the resolution of information that we got back from the monitoring. So that information has now been released within the last month, and some of the high-level findings we took from this monitoring experience. About 7.5, I'm sorry, teragrams per year of methane. That's extrapolated from the hourly methane emissions rate that we found from the overflights, 860 tons per hour. You can see on this slide the range of different emissions we found, the average loss rate across our basins that were measured, and the range of loss rates that we see across those basins. And the last slide I have here on the methane air, the remote sensing overflight experience, is just kind of a more detailed breakdown of both the percentage loss rate that we see across basins, which you can see on the left here, and also the overall emissions in kilograms per hour that we see across a number of the basins that we flew over with the remote sensing instruments. And, you know, I think for us, this has kind of helped to reveal two important use cases for the information that is being kind of developed by the overflights. One, just tracking emissions. I think, you know, what we're seeing as part of this experience is a lot more spatial resolution on where emissions occur, how large they are, and how those change over time. And so those are new insights that I think are additive to some of the information that we've seen from other data sources in this area. In addition to that, you know, we're able to see large point sources of emissions through the overflights. And these are things that can help when they're shared with companies and with regulators, you know, help to really support rigorous compliance with environmental standards and also enforcement. And so it's really serves those dual purposes. So in addition, I'd like to say a word about the methane satellite that EDF recently launched in partnership, again, with a number of others. This is the same instrument that was a part of the methane air overflight campaign. And the goal here is to quantify emissions from 80% of global oil and gas producing regions. So again, this will be a global data platform, freely available access to data. And, you know, the goal here again is really to provide transparency on emissions across oil and gas producing regions over the world. The planned lifespan for methane, the methane satellite is 5 years. And, you know, we really saw this as kind of an important addition to what is already available from a number of other different sources on sort of global satellite oil and gas methane mapping. You know, there are a number of sources listed here, including the Tripomi satellite, that provide really large scale mapping of methane emissions, and then a number of additional sources that are very directed at kind of point source and facility level mapping. And really the hope for the methane sat device is to operate in the middle and to provide, you know, regional scale mapping of methane emissions at a spatial resolution that is, you know, higher than some of the global devices, but broader than some of the point source devices. And so, you know, for us, I think that's particularly important because as we've increasingly looked at the science in the space, there is, you know, a large amount of methane that we see coming from diffuse area sources. And so being able to capture that through these satellite observations is quite important. So in addition to this methane work, I wanted to highlight some air pollution, advanced air pollution monitoring that EDF has undertaken in partnership with Google and Google Earth Outreach. And so there's a dimension of that also relates to methane emissions, but really want to focus on our work on hyperlocal air pollution. mapping, where we have worked in partnership with a number of researchers to deploy air pollution sensors on Google Street View vehicles that have traveled around different cities. The one that I'd like to highlight is a project that we undertook in West Oakland. And here just a number of different analyses that we released, building from the data that we collected as part of that set of air pollution monitoring activities. The first was really just to look at different air pollutant measurements that were collected from those street view cars, black carbon, NO and NO2, with key findings of just the really extreme disparities in pollution that you see across like very limited geographic areas in West Oakland, 5 to 8 times higher median pollution levels in certain areas as compared to others. Our scientists were able to build on that research by using the data and combining it with other information to perform epidemiological studies that look at the risk of cardiovascular disease in elderly residents living in West Oakland, and then to build further on that in analysis that was released in 2021, looking at the health impacts assessments in the area. And again, the goal of this was really to translate hyperlocal air pollution data into actionable information about health risks, and then further into recommendations around action. And I would say for both the methane related data and for this hyperlocal air pollution data, we have used insights that we've gained through the work to advocate for more protective policies and more equitable policies to reduce methane and air pollution from major sources in the area. So apart from EDF's work in this space, I wanted to just highlight some important developments that we see in kind of supporting the broader deployment of advanced monitoring and really monitoring in general, catalyzed by investments in the Inflation Reduction Act. So on November 3rd, 2022, EPA announced the selection of 132 air monitoring projects in 37 states to receive over $50 million in funding. There are a number of really great projects that were funded through these grant announcements, including an air monitoring project in the Navajo Nation and many others. Building on that, in February 2024, EPA announced the availability of $81 million in non-competitive direct award funding from the IRA for eligible states, local, tribal air agencies to improve the monitoring network. And so, there are certainly things EDF and others are doing, and we see this money from the IRA as being kind of a really important additional complement to support the deployment of advanced monitoring devices broadly to be able to assess local air quality across the country. So, as I mentioned at the outset, I work with our scientists here at EDF and get to sort of use the data that are produced as part of the efforts I described earlier to advocate for protective standards. And there are a number of, I think, good examples of how data on large point sources of emissions that many different entities have collected can support compliance and enforcement actions. I wanted to really focus here on some important developments that we're seeing around how these data can be directly integrated into protective climate and clean air standards. And that's something that we see as just another way in which the data can have a real impact in reducing pollution. And we talked about methane monitoring at the outset, and I wanted to talk a little bit about EPA's oil and gas methane standards and how they reflect advanced monitoring technologies in a number of different ways, and then a couple of other opportunities we see. So the oil and gas methane standards are really interesting because they provide operators an opportunity to use advanced monitoring technologies directly as part of meeting the standards. They're an alternative pathway there. In addition to this, and Jane mentioned this in her talk earlier, EPA finalized a super emitter program as part of this that allows third parties who are using advanced monitoring technologies to submit data that they collect using those technologies to EPA. If those data are, show emissions greater than 100 kilograms per hour, EPA will verify the submission. There are a number of guardrails that EPA has put in place to ensure that that data collection is rigorous, but will then submit the data to an operator, and an operator can take corrective action after that. So this is really, I think, in our view, an important development that recognizes that this ecosystem of monitoring technologies provide just a wealth of additional data that can be actionable, and helps to integrate that directly into a set of clean air standards in a way that has guardrails to ensure the data is rigorous and credible, and also creates a greater opportunity for oil and gas operators and others to use the data to support emissions reduction. So it's really, I think, an important model to think about in other contexts. Also wanted to highlight EPA's recent greenhouse gas reporting requirements and the request for information that the agency issued about how to integrate satellite data on methane emissions for oil and gas sources and for landfills into their subpart W greenhouse gas reporting requirements. So this includes questions about spatial and temporal resolution of data, and again is something we see as really an important step forward to use some of the advanced technologies directly in clean air reporting requirements. And beyond those, we see additional opportunities to use models like these in other spaces. So you can imagine for landfill methane emissions, super emitter detections is a way of helping to reduce those emissions. For the National Ambient Air Quality Standards, we're discussing particulate matter monitoring earlier, and EPA has taken a really important step forward there to require more particulate monitors in its recently finalized standards. We think there could be additional opportunities to use satellite data, sensor network data as a way of both informing where you'd want to place those additional monitors, and even as part of a set of considerations around where areas are meeting or not meeting the standards, again, combined with other data. So alongside this really sort of rapid development of advanced monitoring technologies, we're already seeing important developments in the policy space to integrate those technologies, and see that as only continuing going forward, and that will be really important to strengthen compliance, enforcement, and reduce pollution. So I think with that was all I had, and thank you.
Well, thank you very much, Peter. And there are a few questions, and then we'll turn to more general questions. Let's see. There's a question about how the calibration occurs for remote sensing that's just deployed in space. And I don't know whether you have any comments about that.
So it is, and I should, in the interest of full disclosure, I am an attorney, and so I'm translating the insights from our science team here. But part of the reason why we did the initial methane air flights with the same instrument, the remote sensing instrument, as we eventually launched on the satellite, was to do exactly that, to do the calibration of the sensor and do that in a series of overflights at closer distances that we could compare with other kind of ground-based measurements. So in addition to providing kind of more granular information, those early overflights were about calibrating and ensuring the instrument was working properly.
Second question asks for some elaboration on the methane loss rate on the slide, comparing methane emissions. Let's see, my slides just, my questions just moved on me, but All right, so it says, can you explain more the methane loss rate on the slide, comparing the methane emissions across major US oil and gas basins?
Yes. So and I don't know if, I'm not sure if I can get that slide back up. Thank you. Yeah, so this is looking at the data from the methane air overflights in each of the basins, comparing it to gas produced in the basins. And these are methane emissions in kilograms per hour. And so you have on the right the absolute emissions in the basin, and you can see there are certain basins, including the Permian, where we see, and this is consistent with a number of other observations, in an absolute sense, by far the most methane emissions. And then on the left, when you compare that to the gas production in the basin, that's how we get the kind of loss rate. So from this, you can see that there are certain basins that have substantially higher loss rates, even if they have lower absolute emissions.
And one final question on the methane satellite. And the question is, with the data generated from the methane satellite program, does it take into account, the interpretation of that data take into account things like high humidity or clouds that can obscure the readings?
It does, it does. And this will be beyond my scientific ability to explain, but yes, that is part of the interpretive algorithms that will be included in the data release. And I do know that the focus, so the satellite is currently orbiting and producing data. We haven't released any of it yet. The focus of the initial sort of data gathering efforts are on areas where we expect those sorts of issues to be smaller.
And I had one quick question myself about the Oakland project and using Google data. And the question is that process readily replicable in other areas where Google is doing street view mapping? Could this be done in other countries around the world? Because I imagine the Google Street View is done widely.
It absolutely is, and it is it's something that we've replicated in London and a number of other areas, and so yes, it is replicable.
I think we want to now turn to general questions. I have one for our panelists that I wanted to ask first of all, and that's I know that a little before the methane satellite was launched, NASA launched an air pollution monitoring satellite, and I don't know whether any of our panelists are familiar enough with that NASA satellite to give us a little bit of a background of what the focus and kind of data that NASA is gathering. But if someone does have that information, we could share it with our listeners.
I believe the satellite you're referring to is called Tempo. And
yes,
my understanding is it measures aerosol optical depth, which is particulate matter in the entire column, but can also estimate ground level NO2 concentrations, and I believe ozone. And I think, with any new instrument, one thing really doesn't replace something else, it complements it. And it's important to have the ground-based measurements because those serve as kind of validation, but the space-based looking down can provide spatial distribution. of coverage of NO2 or particulate matter or methane or whatever.
Jerry, do you want cover some of the questions that have been asked that we haven't covered already?
I have a few general ones, which I want to ask. One is to Jane, and it's a question of the EPA. I just wanted to know, for purposes of comparison with our jurisdictions in Africa, how often does EPA update the air quality standards, and what informs that update? For team, it's more with respect to ownership of the data emanating from the monitoring networks. And that has been an impediment for many African countries. The few that have managed to deploy monitoring networks in the cities, one, they have to grapple with annual license subscriptions, which are sometimes prohibitive, and therefore sometimes within 2-3 years of deployment, the networks become useless because they don't subscribe and therefore they can't access this data. Is there any way you foresee in the near future that some of these challenges could be overcome? So those are my two quick ones. Thank you.
So, Jerry, I apologize. I don't know the specific answer to that question. So what I will do is get it back to you in an email. Does that work?
Thank you.
Great question, Jerry, and that's a big issue with some of the air sensors as well as instruments. There are manufacturers that charge an annual fee for those, and a couple of options here. One is in the planning stage, owning the equipment, can help. The other thing is thinking about capacity in terms of the equipment. What organizations may have capacity to run this for 5 years, 10 years? That might be universities that have, the capability, longitudinal capacity and time capacity to run things. And it's not just there, it's capacity everywhere that I see in all cities, nations. The effort it takes to run equipment, be it low-cost sensors or be it reference equipment, is a lot of effort. And so one rule is when budgeting, make sure there's enough time invested in that 80%, and I would say even 90%, in the people, in the training, and the people managing data, doing the maintenance, all that. Where we see things go wrong is organizations will take their budget and spend half of it or even more on technology and expecting technology to solve it. It's not. It's going to be the people that solve this, and providing the training and all that. So I think it really starts early in the budgeting process, whether you're a funder like EPA handing out funds, or whether you're a recipient grantee of that funding. Make sure you get that ratio right.
I had a question, kind of a general question about managing the proliferation of data and coordination related to this. So Peter mentioned this a little bit, and that is the kind of cooperation between NGOs and government in the providing data to each other. But as we get more and more data in the system from citizens, from NGOs, from private sector satellites, how should that data be gathered, utilized, perhaps using AI to analyze that data So looking ahead on the data management issue and the data cooperation issue, what would you like to see, or what do you anticipate the future may be as we get more and more data? That is important to make decisions like Peter mentioned on the design of regulation. It's also important for enforcement. It's important for neighborhoods to understand what's happening in their neighborhoods. So anyone want to take a shot at that question?
Happy to start the conversation, but there's two aspects to this that I think are very important that you identified. One is the human factor. There is a need for the folks to still review and ensure data quality, consistency, and the like. Looking further ahead as machine learning and AI evolves, there's always an argument to be made for that deep learning to start and algorithm development to start doing some of that work. But the reality is for the near future that it seems to be problematic. So taking that human factor is important to consider as that technology evolves. That's my personal take on the question, but I think it has to be a consistent look at when can technology take some of the work away from the individuals, yet still take into consideration that human factor to ensure consistency and quality of data.
Maybe I can jump in also. So the question is very interesting, and this can trigger hours of talk. But what the trends I can see myself is that like in any ambient of human activities, the amount of data, as you mentioned, is growing, and it's more difficult to let's say deal with them, treat them. But I mean, there are encouraging improvements. So it's important, first of all, to mention that we have several sources of information and that are complementary. Indeed, from one side, measurements, ground-based measurements, satellite measurements, and modeling. And measurements are very important for checking compliance with the target values that are set by the legislation. But then models are very important also to understand what are the causes of pollution, so the so-called source apportionment, which is important also to define measures to abate the emissions. We have also models that are able also to make scenario analysis and to so make projection for the future. And this is something that measurements cannot do. So you take a model in order to do this kind of estimation. So what I see that is now more and more there is a collaboration between different disciplines. It's data are put together. So now satellite data are combined with the ground-based data, and then are used by models in order to cover areas where measurements are scarce, and to have also projection in the future that supports policy. And so this is, I think, in the future, I see that this will be more and more common. So the integration of several sources of data. For example, here in Europe, we have the example of Copernicus, that is an institution who is dealing with all the treatment of different kinds of data and making this data available to the public. So this is very important. In Europe, environmental information is public by definition. So there is a legislation at the European level. So access to environmental information is a right. And this is very important point, because this is the first step also to protect people's health. And I stop here, but I think that maybe it could be useful to continue ping pong between us and the public.
I'd add just kind of one quick thing. I think it's really application dependent, what data you pull in. In some cases, you want really high quality data and you want to know who's collecting it and what they're doing with it. In other cases, the data may be sufficient for a particular application. And I think there's a fantastic example right now that EPA is doing that's called the fire and smoke map, where they have the reference air quality data that's run by the state and local agencies, and they bring in air sensor data and put that together for a nice comprehensive picture of what's going on in terms of PM 2.5 and wildfires throughout the United States. It's a great example. For that particular application, air sensors are good enough. And yeah, thank you, Cora. So she just put a link to that in the chat, and it's worth checking out. But I think it's going to be application dependent and probably that way for the next 10 to 15 years.
Yeah, and maybe just 2 quick points building from what Tim just said. I agree. Like there are some applications where, you know, you're really looking at kind of a weight of the evidence type approach. EPA does this regularly. And so, you know, it's quite a bit easier to pull in a range of different information there when it's supplementing, you know, existing information versus, you know, where you're looking at a direct replacement for information. You might need to have some different parameters and quality controls around it. The only other thing I would say is, like, we often think about, I sometimes focus on the technology and the development of the technology in isolation. I think there is a piece of this that is reflected in what EPA did on the oil and gas standards side, where there is opportunities to change policy too, to ensure that the two kind of talk directly together.
Jerry, back to you if you have questions. You wanted to, I have the panel.
There are a few pending in the Q&A box. We can try to answer a few before we get to the end of this. So number 1 is, for states and local governments, is it more cost effective to outsource air quality monitoring? Is there a benefit of partnering with NGOs to mitigate the costs? Are there any examples of this?
I know of none in the United States. There may be a little bit of outsourcing here and there, but you know, it's important that these agencies build capacity and have the institutional knowledge to run things for 20, 30, 40 years, so that we can ensure that the data are high quality, can be used for things like policy, regulations, etc.
The next one, I guess, is for Peter. Can you put a street grid or at least county lines on the methane sat so that it is easier to navigate in rural locations like the Permian Basin?
Yeah, yes, there are, and that's the case with the methane air data that is already out. But yeah, the spatial resolution of methane sat, you know, should be able to accommodate those sort of geographic lines.
And a follow-up, I think, is with respect to ground level monitoring and whether this is used to complement satellite monitoring.
Is ground level monitoring used to complement the satellite? Is that the?
Yeah, so the question is, are ground level monitoring technologies used to complement or supplement the satellite data?
So we're not using that directly, although I'd say, like, we see certainly a role for those technologies as well, given the detection limits of the satellite technologies, which will, you know, allow us to understand area source emissions at a relatively granular level. But the detection limit is such that, like, you know, it is important to complement those with ground-based technologies.
Thank you, Peter, for that. Lee, I see we are closer and closer to the end, so I hand it back over to you.
I have kind of a follow-up question with for Peter on non-governmental monitoring, and the step that EDF took is a pretty big one for an environmental organization to invest in the technology, and obviously didn't do it by yourself with several partners. But do you see that as an area where there's likely to be new sources of monitoring information with as technology changes and problems are identified? Do you see the nonprofit sector or perhaps even some of the private sector data becoming more commonly available and used over the next few years, or is methane kind of a unique issue by itself that it is not the front end of what might be a trend for a significant increase in non-governmental monitoring?
Yeah, I definitely see increased opportunities there. This is also in the methane and greenhouse gas space, but Carbon Mapper is, has launched its own effort. So we see kind of another example of additional satellite monitoring in the non-governmental space there. I know the Tempo satellite that was mentioned earlier is satellite air pollution monitoring, but it does seem that there are opportunities to extend this in other ways and in other sources, just given the kind of richness of information that it provides and the transparency across kind of wide geographic regions to support the efforts that state and other actors are taking in this space.
And Jane, what do you see the expansion of non-governmental monitoring data? What do you see that it may mean for EPA and the way it collects data, uses data? Peter already has talked about some of the kind of collaboration between EPA and EDF related to data that they're collecting. So how might this affect EPA over the next few years?
We certainly appreciate good quality data, and getting it from different sources, whether it's localized or more of a broad view, certainly help us in doing our analysis and being transparent in what we're seeing with different communities. We do like combining data where we can to sort of see where potential issues are and help us with our work. So certainly it's something that is welcome, and we are, whenever we can, work closely to identify possible areas of collaboration.
And then maybe I'll close on one question, and that is what are the circumstances where there are still really important gaps in monitoring that need to be filled, or maybe are only partially filled by some of the low-cost sensors or other monitoring data? What are the gaps that are important? And maybe Claudia, we could start you if you see some of the potential remaining gaps in monitoring, whether it's the neighborhood scale or particular types of emissions or industries.
Yeah, the point is that I mean, there is a correlation between cost and the quality of the data. This is unavoidable. Also, not only cost in terms of equipment, but also the preparation of the staff which is dealing and interpreting data. But the AI, for example, can help in this interpretation of data, maybe reduce certain kind of costs. So the fact that the high, as Tim mentioned, putting together as a fabric of the network official data together and complemented by low cost, this could be a frontier that should be explored. And it's also many official institutions for monitoring are moving into the directions of incorporating the low cost sensors. And I think that maybe the combination of most sensors into a single device is helping also to improve and, let's say, deal with the efficiencies or limitation of the different types. And this is something that should be improved. But it's important also the information about what can be done with the low-cost sensor and what cannot be done, or the importance of taking care of good quality where the good quality is needed, as Tim mentioned. Not always, I mean, the best quality is necessary, but it's important to be aware of what kind of data you have in front of you.
Thank you. Jane?
Sure. This is a very broad question because we don't know what we don't know, and we always try to see what we're trying to tackle, whether that's climate change or health impacts. So depending on what that is, the gaps that we're trying to identify, certainly there's everything from fence line monitoring, air toxics monitoring in urban areas. The gaps in tribes, for us, that's a pretty big one and tricky because they exist outside of our monitoring network all the time. So building those partnerships and identifying those gaps is incredibly helpful. So having that pre-conversation that we had with you, Lee, for you describing the issues that Jerry's trying to tackle certainly helped us understand some of the gaps that we have and trying to identify them. So it's a tough one. It's always good to get more data, but sometimes it's identifying those gaps that's super important and the issues that we're trying to tackle.
Tim?
I think the thing that I would focus on is more hyperlocal and measuring more VOCs in different compounds and being able to speciate those. That's where I think I would put money and effort right now, given what I see.
Great. And Peter, you get the last word.
Yeah, I think I really appreciate it, and thanks for the great conversation today. Agree with others. I think the hyper local, really drilling down on some of the spatial pollution variability that we're seeing in areas which can be quite extreme, and then also, and for different sources, the temporal variability that we're seeing for sources that are intermittent but can be quite significant. So kind of building information out in both of those areas.
We are exactly at 1 p.m. Eastern time. So thank you all to our panelists. It's been a wonderful presentations today, and I think we've all learned a lot. So thank you, Jerry, for co-moderating with me, and please all have a good afternoon or evening, depending on your time zone, and thank you for joining us.
Great, thank you.
Everyone, bye.
Okay,
Bye-bye. Thanks.
Thanks so much, everyone.